Let's suppose we have this system of equations we have here, where here these u1, u2 are and un are unknown values, and all the rest, this m1, 1, m1, 2, m1n, and the q1s, or these m1s and the q1s are known values. So this is a system of equations where the unknowns are expressed by u1, u2, up to un. So you have n unknowns. Of course, this system of equations, they can be written in this way, in the matrix way. So here we have this, the matrix M is multiplying some U column here, and the resulting one is going to be the Q1. So these Q1s are known values. The M matrix is going to be a known matrix as well, and these U are the unknowns. And the aim will be to have a solution for the U values that satisfy this equation here, or this matrix equation here. This is actually what we do have, or what the kind of equations that we need to solve in the implicit method, or in the Crank-Nicholson method when boundary conditions are included. And we have a straightforward way of doing that, of course. If we do have this matrix representation of this equation here, of course, we can get the values of the u function basically just importing the matrix. So you have the u column here, which are the unknowns, is going to be the inverse of the M matrix, which is going to multiply to the Q vector. This is actually what we did for the implicit method, or for the Crank-Nicholson method. Where there, for example, we do have this, that will be in the fully implicit method, or in Crank-Nicholson method, we do have these U vectors are the ones evaluated at the time j plus 1, and we had all here on the right was evaluated at time step j that was known. So here on the right is already known, so multiplying the matrix we do have here, we can get at the end a column with known values here. And this u vector evaluated at time j plus 1 is the one which is unknown in this Crank-Nicholson method, for example. And of course, we can get this value just importing this matrix and sending it to the right. But the thing is that multiplying and getting inversion of the matrix, when the matrices are huge, it's not efficient. It's important to analyze if there are other ways to solve these equations without the need of the inversion of the matrix. It's going to be important whenever your matrix is huge. And we're talking about time, you can save a lot of time if you are taking care of these fine details. And of course, there are some ways of doing that. And for example, here we're going to see some of them, some methods. And the first one that we are going to check here is the one which is called the Jacobi method. Okay. It's important to take into account that this Jacobi method is going to be an indirect method. So basically means that we're going to solve it iteratively, and we'll see later what does it mean that we are going to solve it iteratively. And we have to solve this matrix equation here in order to get the expression for the values for the u vector here. And the thing is that the drawback of this method is that the solution will never be exact. However, it's very important. You can always get that values to whatever accuracy you want. They can be as accurate as you want. So that method is going to be solved iteratively, and you can get the solution as accurate as you want. But it's never going to be, okay, in principle, will never be exact. So what we're going to do. So first, we're going to start with this matrix representation, okay, with this system of equations here. And the first thing we are going to do here, we are going to leave here on the left of this equality here, we're just going to keep the elements here we do have in the diagonal. So first here, the first equation here, we're going to keep m11 times u, and all the rest here, we're going to bring to the right. That's what we have here. So here in the second one, we are going to keep this one on the left, and all the rest, which are these ones, we are going to bring it to the right, and this is what we do have here. And the same with the others. That's the first thing. And the second thing is that here here on the left, we are going just to clear u1, u2, and to un. And for that, we are going to bring this m11, we are going to bring to the other side, and just basically we are going to do that just dividing 1m11 over times all this. And the same with m22, and so on and so forth. And this is the expression, this is the new way of writing the same system of equations, basically. So here on the left, we have u1, u2 up to un, and which is expressed in terms of, in the case of, for example, in the case of u1, you have writing that in terms of u2 up to un. How can you use that? Because in principle, yes, it's true that you have clear here u1, but as you don't know the values of u2 up to un, that's useless. You cannot use that in order to get the value of u2. Of u1, and the same for u2, and the same for un. So how are we going to use that system of equations in order to get from here the values of these ones, of the u vectors? Okay, here's the trick of the Jacobi method. So the trick here, we are going to use and solve that system iteratively. What does it mean? Basically, it means the following. We are going to start with some initial guess for the u vector. Some initial guess for u1, some initial guess for u2, some initial guess for un. And we're going to plug that values here on the right-hand side. And that's going to be the ones that we are going to use in order to get the new ones, the new u1, u2, un values. That, of course, these ones are going to be different from our initial guess. Okay? So what's going to do next? We are going to follow, again, an iterative procedure. What does it mean? We are going to take the new values that we have obtained, plug them here on the right in order to have a new u1, u2, up to un values. And, of course, they are going to be different, but probably they are going to be closer to the exact ones. So again, we are going to plug them, the new ones here on the right, in order to have a new ones here on the left. So we are going to follow that iteratively procedure in order to get the u values as accurate as we want. How do we know that? So we can check, for example, we consider all the values, for example, let's take the first one, and see if the new ones, for example, the ones obtained in the iteratively step j plus 1, and take the absolute value, consider obtain the difference between the two iterations, and see whenever they are all of them, not just the first one, for example, when just all of them are lower than some value that we are going to call epsilon, for example, that will be your tolerance. You have to here consider your tolerance. For example, I want it to be lower than some value. Right? Actually, it's better to consider not just the absolute value of the difference, but the absolute relative difference, which basically is just this one divided by the absolute value, for example, of this one. So whenever the relative difference, which is this one, is lower than some specific value, which could be for example, 3 to minus 3, 10 to minus 3. For example, this is something that some value that you have to consider to be accurate. For example, if I consider to be accurate enough whenever the absolute relative difference is lower than this one, so whenever it happens to all the different components of the u vector, then I can stop the iterative procedure and consider that I have already reached the exact values, considering that accuracy that I have considered to be enough. So, as you can see here, that's an iterative procedure. It's an iterative procedure that I think you already know here. What does it mean, iterative procedure? You put some initial guess here in order to have a new ones. You put these new ones here on the right in order to have a new ones here on the left. You procedure this iterative procedure. Actually, here this subscript j means the level of iteration that you are considering. For example, the first one will be j equal to be 0. That will be our initial guess here. And therefore I'm getting the u1 for the u11, that this one will be the ones coming from the first iteration. Then you are applying here for j equal 1 the ones that you have obtained here in order to have the u1, 2, those coming from the second iteration, and so on and so forth. Whenever they are reached, the difference, the relative difference is reaching to some value that your tolerance to be, in order to be them to be accurate enough. This is the Jacobi method. Actually, it's interesting to see that this expression here, this system of equations, they can be rewritten actually in a more shortened way. For example, all this n here will be here, n will be subscript will go from 1 to n, that will correspond to all different equations we do have here, the same as the one we do have here. And these summations, all these, the summation of different products of m times u, you can see there are n minus 1 different summations here. And actually, the only one which doesn't appear in this summation here is the m times un. So that's why we can write this double summation here in the following way. That j will go from 1 to n minus 1, okay, and then it goes from n plus 1 to n. So the one which is missing this summation actually is this one, because this is the one that appears here on the left, that's connected here when the term that appears on the left, and this factor which is multiplying with all of this. So this is actually the Jacobi method, an iterative Jacobi method that of course depends on this initial guess. And as we have said at the beginning, it's not accurate, but it's as accurate. It's not exact, but it's as accurate as you want, because you can keep the iterative procedure until you reach the tolerance that you are required. And it's important also to have in mind that this set of n equations, they can be written in this simplified form.